Hello, my name is Julfan Hafiz Farezza with my partner Mr. Arad Gani Safitra and Mrs. Lohdidiana. Here I want to explain you about our paper, the 3D CFD simulation analysis of drying cabinet at transient condition. Okay, for the background of our research is one of the renewable energy is solar. It could heat air for drying food, meat, fruit, and vegetables. It was called a solar air heater. In a solar air heater, a drying cabinet was needed. It had a function to collect hot air from the solar collector. The hot air would heat food or vegetables until it became dry. Food or vegetables were usually arranged on some tray inside the drying cabinet. This paper did a simulation of the drying cabinet in 3 dimensions. It used computational fluid dynamics. In this study, the geometry of the drying cabinet used 5 trays. This simulation was a transient condition with time step 0.01 second and 30,000 number of iterations. This paper had many purposes to predict some phenomena, such as air vector velocity, air temperature distribution, air velocity streamline, change of air velocity, temperature, and pressure inside the drying cabinet. There were several steps in this simulation. The first step, we create the drying cabinet geometry and mesh. There were 5 trays inside the drying cabinet. This figure shows meshing for the drying cabinet. The meshing type was tetrahedral. The wall made from acrylic with some properties. The outlet section was a pressure outlet. In this section, the ventilator turbine was installed. This simulation used the transient method. The time step is 0.01 second with the number of iteration 3200. It means its running start from 0.01 second until 32 seconds. But this paper only present simulation result at 4 seconds, 8 seconds, 16 seconds, and 32 seconds. The air velocity was drawn by vector when time equals 32 seconds. It can be seen in this figure. It's shown in the isometric view. Based on the figure, the air velocity in the inlet section and the outlet section was high. The air velocity from inlet section from x equals 0 meter to x equals 600 meter was uniform. It was 0.01 meter per second. It is signed by the same yellow color. In outlet position, the air velocity became high again different. It because the ventilator turbine was installed in outlet section. In position x equals 0.6 meter to x equal 1.2 meter and y equal 0 meter to y equal 1.33 meter, the air velocity was rather low. It because of gravity acceleration, and there are several trays inside the cabinet. The tray became a disturbance for air to went up. It was signed by a green color vector. The airflow near the wall had a blue color vector. It means low air velocity. It because the wall had a temperature the same with ambient temperature. The air velocity vector were plotted in the middle plane for time 4 seconds until 32 seconds. The result can be seen in this figure. It had a purpose to know the different airflow patterns from the time to time. Based on figure, when 4 seconds, the airflow was a smooth pattern. The air entered the cabinet smoothly. The same pattern happened until 8 seconds. It means air flowed from the inlet section to the outlet section directly. When time is equal 16 seconds, there was small reattachment in the bottom corner of the cabinet. It means there was a mixing process inside the cabinet. The reattachment became weak when 32 seconds. It caused air current could be mixed with new air. The air temperature distribution were plotted in the middle plane. It had a purpose to know different contour from time to time. It can be seen in this figure. At 4 seconds, the high air temperature was in the middle position, and air near the wall had a low temperature. At 8 seconds, in the top corner, there was a small discoloration from red to yellow. The discoloration looked like yellow fog. It means the top corner was an initial position for air temperature change. The discoloration grew up from time to time until 32 seconds. It means air temperature inside the cabinet underwent the mixing process. In this simulation, the wall temperature influenced by heating process. Based on figure, the inlet air temperature mixed wall temperature. It was because the air touched the wall. It is called conduction heat transfer. The air temperature in each tray was analyzed. There were tray position and time change. It had a purpose to know the air temperature distribution from time to time and the optimum tray position. It showed in this figure. It showed hot air position was in the center of all the tray. It was because the tray had many holes in the surface. It caused hot air from the inlet section out through directly. Meanwhile, air temperature were low in the corner edge of the tray. Based on figure, the air temperature distribution was not uniform at 4 seconds. The air had high temperature in the middle of the cabinet, but the air near the wall still had low temperature. At 8 seconds, the air temperature distribution was still not uniform, but the cold air temperature near the wall started to mix. It showed by discoloration inside the edge. At 16 seconds until 32 seconds, the air temperature distribution were more uniform than before. It means the mixing process would happen if time was at. Based on figure, the optimum tray position can be known. The tray in the bottom position had more red color than the others. It means tray in the bottom position was optimal. It because the position was near to the inlet hot air. In this figure, it shows air streamlines in each tray at 32 seconds. It had a purpose to ensure that the tray in the bottom position or tray 1 was optimum. Based on figure, air velocity streamline in tray 1 show 2 vertical in the tray surface, so it could increase air temperature. In this figure, it shows many parameters in the center line at 32 seconds, such as air velocity, temperature, and pressure. Based on figure, the air velocity decreased when air touched tray surface. It made backflow. The air temperature inside the drying cabinet decreased from Y equal 0 meter to Y equal 1.55 meter. It because of temperature condition from the tray and cabinet wall temperature. The air need much time to heat the cabinet. The highest air temperature was 232 Kelvin in Y 0.2 until Y 0.3 or in elbow position. Based on figure, the optimum tray position could be known. In tray number 1, the maximum air temperature was 322.6 Kelvin. It was tray number 1 because of the position near with inlet section. Based on the figure, the air pressure inside the drying cabinet decreased slowly from 0.03 Pascal to 0. It was because of the open system for the drying cabinet. When air touched the tray the same with velocity, air pressure would be decreased. For our conclusion, the optimum tray position was tray 1. It was at the bottom of the drying cabinet. It because of the position near to the inlet section of hot air. The air temperature distribution could be uniform if the number of iterations was increased. That's all. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. First, I would like to say thank you for the time and the opportunity. My name is Gilang Muhammad from part-time engineering branch, and I will represent our research about tensile test simulation for polymer composite. The author of this paper are Ms. Diana, Mr. Argani Hafitra, and me Gilang Muhammad. Introduction. There are many kinds of waste such as polymer. It always increases every year. One solution to reduce waste is to make new material. It can be used for the building material, vehicle body, and storage tank. The material must have mechanical properties to know the ability of material according to its use. There are some previous research about tensile tests of composite material, and there are some research with numerical simulation and experimental study were needed for reference to this study. And the main process of this study are to predict and compare mechanical properties, especially tensile strength for polymer composite by using finite element analysis simulation. In this study, there is three various papers from polymer. The polymer were polyethylene terephthalate or PET, high density polyethylene terephthalate or SDPE, and low density polyethylene terephthalate or LDPE. The study results are tensile stress distribution, and strength distribution. Based on the result, it showed the new material can be classified according to the ability material to hold the tensile force. Is to use. The common parameters that used in the research about tensile strength of material are stress and strain, where stress is the reaction that arises in a part of specimen to withstand the load given, where in the mathematical form is force divided by area, and strain is stress or pull is the quotient between increasing length and the initial length. The specimen used Sistem E646 tensile test standard as the geometry standard. It had 200 mm in length, 20 mm in width, and 4 mm in thickness. The working principle of tensile test is the tensile force application. The test object is clamped at the both edge, and the tensile force is applied in one position in an upward direction as shown in figure B. And the other edge, the condition is stationary and or fixed support. The specimen was formed from several layers of material consisting of metric and reinforcing fiber as shown in figure B. There are 3 layers of metric and 2 layers of fiber. The specimen condition before and after installs are shown in the figure A. The specimen after the tensile test had more length than before test. It was called by elongation. The elongation is important to determine the strength of material. Material properties. The material properties were needed for simulation. The properties can be seen in Table A for PET, Table B for SDPE, Table C for DPE, and Table D for resin. Mesh and parameter setting. The mesh geometry used hexahedral structure. It consists of 11,000 nodes and 5,000 elements, as shown in figure A. The simulation used node displacement method to represent tensile force that had been explained based on the tensile test procedure. Figure B shows the selection setting and the specimen direction. The nodes at section A of the specimen set as fixed support nodes, and the nodes at section B set as displacement nodes which move to the x positive direction. Stress and strain graph. The following are tensile strength graph of PET, SDPE, and LDPE that was obtained from FEA simulation. Based on the graph, now the maximum stress value of PET composite is 471.06 megapascal and the maximum strain value at 0.461%. Then, maximum stress value of the SDPE composite is 452.1 megapascal and the maximum strain value at 0.506%. Well, the maximum stress value of the LDPE composite is 430.75 megapascal, and the maximum strain value at 0.796%. As we know, based on the explanation of three tensile test graph, it could be concluded that the composite material that had the greatest tensile strength was PET composite and the lowest was LDPE. Stress contour. The stress contour or stress distribution were plotted at the maximum stress. The color difference show the difference in the value of the stress that occurred in the specimen. The greatest stress concentration was found at the base of the reduction section that was pulled in the x-positive direction. It is due to change in the shape of geometry from the reducing section to the grip section, which caused accumulated pressure. The stress concentration position was in the right x position. It was in the moving area or point B. The material would be broken due to the composite material was brittle. Strain contour. Same as stress contour, the strain contour or strain distribution were plotted at the maximum strain. The maximum strain occurred when the composite material were broken. The fractures in the specimen were located at the location with the highest stress concentration. The strain concentration position was in the X position. It was set by yellow color. After the material broken, it usually extended to the composite material was brittle. The strain distribution was different for epoxy and composite reinforced HDPE. It was because the composite had high elastic deformation. Conclusion. The composite with PET fiber had the highest tensile strength of 471.06 megapascal, and the lowest tensile stress was 430.75 megapascal for the LDPE fiber. The simulation result also presents the stress and strain contour in the specimen surface. The simulation setting can be used as recommendation for the tensile test simulation method, especially setting correct position in the H position. It's due to the correct position usually happen in actual conditions or the experiment for composite material in real conditions. And this is my reference for this study. Thank you for your attention, and wassalamualaikum warahmatullahi wabarakatuh.